Okay, so this is the second part of Psych 522 on November 12th. Okay, so remember before the break, we were talking about this structural equation modeling confirmatory factor analysis framework. So we've talked about that null hypothesis and how we're trying to reproduce that covariance matrix. Now, one thing to kind of realize here is the EFA model, right? The EFA that we've talked about. If you were to put these things into Venn diagrams, right, which one would have the bigger Venn diagram? Would it be the CFA or would it be the EFA? Well, you probably want to do this and say, well, there's your CFA, okay, of which the EFA is a special case. Why? Well, because the exploratory factor analysis, as we've talked about, it has certain parameterizations in there that are kind of fixed in place. Whereas with the CFA, you have more control over virtually all aspects of the model. And so in the EFA, you kind of, you just take it what the program is going to give you. But the CFA allows you a little bit more freedom in that way. So, in my CFA right here, there's nothing preventing me from allowing EXTR to be a function of all these variables and just getting rid of this entirely. So I could have run it that way as well, but I chose to run it this way. And again, well, just like we talked about before the break, just because a model fits doesn't necessarily mean it's the right model. It just means that it's reproducing that covariance matrix. And many different models can reproduce the same covariance matrix. Right? That's important to understand because otherwise you start to think, wow, I found the factor model. And that's not true at all. The factor models like this often appear in the school psychology literature, especially when they're trying to get the determinants of IQ, kind of like what's the correct factor model for IQ. And oftentimes you see these types of things and authors are debating, is it a 2-factor structure? Is it a 3-factor structure? Is it a 4? And that's fine to have those discussions, but just so long as you're aware of the inputs that go into the modeling before you actually run the model. So there's a lot of parameterization in there. And I more or less think it's kind of a mistake to kind of try to determine whether it's a 1 or a 2 or a 3, because there's so many details in the parameterization. You could have a 3-factor model fit almost just as good as a 2-factor model. It's kind of like these researchers are looking for that skeleton, right? There's that skeleton underneath and there's the person digging with the shovel and they're trying to uncover the factor solution. Well, based on what we know from modeling, we know that different models can come close to reproducing the same data. So we just have to be careful in how we interpret it. The other idea before we continue here is we were talking about that chi-square test. And what do we know about chi-square tests and significance tests? Well, we know that they're going to be influenced by sample size. Right? So all of those things that we've talked about for sample size problems with the chi-square test, with the t-test, with the z-test, and all that stuff from previous courses, that's going to apply to this as well. So when you read the SEM literature, they're going to talk about that problem like it's a novel problem. They're going to say that chi-square test is not good because it's sensitive to sample size. But you're going to know that that exists in a whole bunch of other tests as well. So that's one reason why the chi-square test is not always the best indicator of model fit because of that influence of sample size. So when we're looking at those previous measures of model fit, like the RMSEA and the Tucker-Lewis, those are also used in confirmatory factor analysis models, and they help absolve that sample size issue. And ideally, when you're looking at these things, you'd like to look at a variety of measures of model fit, not just one, but beware of that chi-square test because of that influence on sample size. Okay, well, here's a hierarchical, higher order factor analysis model, confirmatory factor analysis model. Now it's higher order, or you can say hierarchical is fine as well, because this particular factor here is predicting this factor over here. So they're, that's that higher order idea where you don't just have one factor solution, you have a one factor predicting another factor. And again, there's nothing preventing you from doing these things, but you should have a theory as to why you want to do it. Okay, and that's important. If you don't have a theory for doing this, then it's really not worth doing, because you can run this type of factor model and get a good fit statistic and say, wow, it fits well, but maybe another model fits just as well. So, trying to defend why you have a hierarchical factor idea here should come external to the model fit. The model fit is not enough for you to justify that. And those are those subjective components of factor analysis that you should keep in mind. So, and you think about this too, you think about, you got one factor here, you got another factor, another factor, another factor, starting to get complicated, right? It's starting to get complicated. Then you have to think, is that my goal? Is my goal to make a model complicated? And then you have to remember Occam's razor, right? Occam's razor says the simplest solution is usually to be preferred, right? Usually to be preferred over more complex solutions if they basically provide the same information, right? I think it's with 2 C's, I'm not sure. Occam's razor. Simpler is better. So imagine if you fit this model and you looked at the model fit like the RMSEA or the Tucker-Lewis or the CFI or other model fit statistics, and you say, wow, this fits really good. But then you found that, you know what? This one actually fits pretty good too. Or maybe this one combined with this one. Well, maybe this is the better model. Why get complicated? And what happens in structural equation modeling is sometimes researchers make them so complicated because it starts to be like a fun thing, right? Hey, let's add a path here. Let's do this. Let's do this. And it gets way too complicated. Simpler is better. Always remember that. The other concept we need to talk about here is the concept of identification. Okay, so ID, identification. Whenever you fit a model like this, you want the model to be identified. Okay, you want the model to be identified. And what that means is that your parameters that you're estimating in the model need to be able to be estimated. So when you set this to be estimated, or this one to be estimated, your model has to have enough information in order to generate an estimate for it. Now, what that means is it should be able to get an estimate that's basically unique. Okay, that's basically unique, that I can say, you know what, I've generated this estimate and it's equal to 0.24. I generated this estimate. Sometimes the model is not identified and it will not be able to provide a unique estimate for the parameter. Now, what does that mean in terms of, what's the concept here? Well, let's consider a simple case where we have y is equal to f at x. There's a function statement. 4 is equal to 2x. If we look at this equation right here, and we said, well, let's solve that equation, right? X, we can solve for x is equal to 4 divided by 2 is equal to 2. In other words, x, the value of x here, is going to provide the result of 4 here. I can get a unique value for x, right? I can get a unique value for x. In other words, I can say that that value for x is identified. I can get a unique value for it. Well, if I have an equation like this, x plus y is equal to 10, well, I can't get a unique value for x. Okay, I cannot get a unique value for x because it doesn't work the same way as I have in this equation here. I look x plus y. Well, wait a minute. That kind of depends on what the value for y is, and y can be almost anything it wants here as well. So if I try to solve for x here, right? I'm going to run into problems, and I'll say that that parameter that I'm trying to estimate is not uniquely defined. In other words, it can be a whole bunch of different things depending on what the value for y is. When we say that we cannot find the value for x, we're basically saying that's not identified. And if you have unidentified parameters in your model, then eventually, the model is not identified. It's not identified. It's not going to work. You're not going to be able, you're trying to basically estimate too much information, right? If you're trying to estimate x and you're trying to estimate y, well, the model is going to say you're trying to, you're getting greedy. You're trying to estimate too much. So then what do you say? You say, well, I understand. I'm being too greedy on estimating too much information. Where's my priority? Well, maybe my priority is really to estimate x. So how about I fix this to 1? Kind of like this idea here, where I had a value for, say, another variable. If I fix this equal to 1, then I can get an estimate for x. And that's where those constraints, we say that we're constraining the value for y equal to a particular value. So this is a very simple situation, just using a simple equation, but that's the concept of when you're working with these models, that sometimes, the software will say, your model is not identified. You'll have to fix a parameter or two in order to identify the model. And here's an example where this variance, we're setting it equal to 1. And we saw other examples previously where we set some of the paths equal to 1. And those decisions to set certain paths equal to 1 are usually based on theoretical grounds. Like, I'm not going to estimate this variance. That's going to help identify the model. But again, you realize that subjective component. It's not like just taking a model and testing it. You're actually having to input certain constraints into the model often to make sure that you identify the model and that you can actually run it. And when you look at this idea, you see that you have more control over what goes into the model because you're now adjusting the parameters. You're now adjusting the parameters based on what you want to estimate versus what you don't want to estimate. Okay. So in this particular model, it's a higher order. So this one here, predicting HRBR, etc. And then we have this one predicting the observed variables here. So we say EXTR has these particular variables load on it, this one, etc. Now again, these here did not have the choice, right? You hypothesize that they're going to load here. These here, you hypothesize that they're going to load here. So it'd be a mistake to say that EXT3 was not given the opportunity to load here. It would be a mistake to say rather that that loading is poor. No, it was never given the opportunity because it was specified in advance. Okay, so let's move on here. And this is where Meir talks a little bit about that identification issue right here that we were referring to, about identifying those parameters right there. So when you think about this, you're thinking about this in terms of restrictions, right? Restrictions. And the idea of restrictions, again, doesn't mean like a lack of freedom. It actually means you have more freedom. It's kind of like a paradox, right? If you're allowed to place restrictions on a model, if somebody's given you that power to place restrictions on a model, then you are exhibiting freedom. And you're most likely in the area of pretty sophisticated modeling, which SEM is, because you're actually deciding what to fix and what to free. So that's why talking about fixing the loadings or restricting the two loadings to be equal, you can also do that as well. And that's going to help out too if you need to make your model identified by making two loadings equivalent. So it's kind of like the less work that you give the model to estimate, well, it's going to help it be identified in that way. the imposition of constraints, right? You impose constraints, and you do it because you have the freedom to do it. Now, when you look at that, you say, well, how is that different from previous modeling that we've done? Well, when we do things like ANOVA modeling and stuff like that, we've never talked about it before, but a lot of those models come with prepackaged restrictions. Okay, they come with prepackaged restrictions. And in the ANOVA, for instance, we have something called usually the sigma constraint. So remember in our ANOVA model, when we talk about a grand mean over here, right? Remember our grand mean? And then we have a mean here and a mean here and a mean here. Well, remember that we parameterize that model so that the sum of those deviations equals to 0. This is going to take some of you way back to Psych 521, 520, but the sum of those treatment effects, the sum of those sample effects were equal to 0. And we never talked about that as being the way the model is set up, but it is. The model was operationalized in the way that the sum of those effects is equal to 0. So in other words, there was a restriction placed on the ANOVA model. We were just unaware of it because we never talked about it in that much depth. But there was a restriction, and you can operationalize the ANOVA model in a different way as well. So the idea is that when we've done modeling in the past, or when you've done modeling in the past, you've come across restrictions. They were just built in to the routine. Here you have a little bit more freedom, and we're kind of approaching the idea where kind of like the widest scope of statistical modeling is that you're imposing and you're freeing. And that's what statistical modeling is the imposition of restrictions on parameters, or allowing the algorithm to estimate and get as close to those parameters as possible. So when you look at this model once more, what you're doing here is you're imposing this confirmatory factor analysis model, and then you're coming up with a good estimation technique like maximum likelihood to try to get this matrix to equal this one, right? So this is your estimation method to do this job. Now, the goodness of how good that actually will fit will depend on what's in here. And that is what you're putting in your theory. That idea may seem a little bit similar to even the idea of least squares regression. Notice that what do we do in least squares regression? There's your data. There's your model. What's the model here? What's the line? It's kind of like the theory, isn't it? Right? There's your parameter vector. Well, what's the parameter vector in regression? A, B. Intercept, slope. Those are the things you want to estimate so that you can generate that line. But nonetheless, you believe that the relationship between X and Y is linear. That's why you're estimating a line. Okay, so you see that some similarities here. And when you get to the structured equation model, it just generalizes a lot more. Now, let me draw one more parallel here. In the regression line of X and Y, watch how this is going to connect here in a second. Watch this. What if I did this? Set the intercept equal to 0. You set, I'm going to use the word set, the intercept equal to 0, so that it has to pass through the origin. That we would rarely ever do in the typical regression because we'd have no need to do it. But you can imagine if we did that, that would be like saying do not estimate the intercept. You are setting it in advance, kind of like you're setting this variance to at a particular value, or kind of like if you set this path equal to 1, you're setting it at a particular value. That's the same idea. After you do that, then you allow the algorithm in that case, usually least squares. It could be maximum likelihood as well to estimate how closely you can get that line to the data points. And then you get an error function, right? The sum of squared errors. Same idea here. This is just a little bit more general, and it's a little bit more explicit in terms of you getting to choose what you want to model. Okay. Okay, so this particular model here, and you can look at some of the summary statistics. Part of the last, well, the final exam will feature a little bit of this, of getting some of that R code and some of the results to make some sense out of it. But you can get some of the summary statistics here, and you'll see it's not printed out here due to space in the book. But the CFI, which is a measure of fit, is equal to 0.95, which is pretty decent, relatively speaking, in terms of what CFI could come out to be. Even values of 0.90 are not too bad. You don't want it to be too low. There's your RMCA, which we've talked about. And this is the standardized RMR over here. So it also gives you a confidence interval. So again, fit statistics, how well does this model fit? And if you go back and you look at our RMCA, you're looking at how well is it producing that covariance matrix, and it's making explicit in that formula that we talked about. One further note just to make about this confirmatory factor analysis before we leave for it is, again, I want to stress the idea is there's nothing experimental going on in here. Right, so you have to ask yourself really from a critical point of view, and you have to be critical of these things, especially when you see big models and things like that. You have to ask, it's like the COVID model, predicting the number of deaths. You have to say, wait a minute, what went into that model? What's going on here? There's no experimental controls in here. So really, of what value is this providing you? And it's reasonable to ask that question. Even if you found a factor structure, so what? What do you do with that? Right? And you want to avoid presenting to a group and not telling them the value of your research. Like, why is this value? Why should we get excited about this? And if you can't convince your listeners as to why this is valuable, you have to ask yourself, what kind of a research claim am I even making then? If you can come up with a whole bunch of different factor models and you can name these whatever you want based on your theory of how the loadings load, what's the utility? What's the pragmatic utility? And if you're outside of an experimental design, it may be hard to justify that sometimes, especially based on the nature of the variable. So always be aware of that the model can get very sophisticated, but it's still the design issues that matter the most in anything. Okay, so now we're ready to talk about path analysis and structural equation modeling. A little bit about its origins, and you read the origins of causal modeling previous to this, and you have a guinea pig here, you have a guinea pig here, and the guinea pigs get together and produce an offspring guinea pig. Okay, so we can say we have a path model here and put coefficients here. These are usually standardized regression coefficients. They could be raw as well. And we say this guinea pig, there's the mom and the dad, they have a baby and it's the offspring over here. Well, when you look at something like this, it's reasonable to ask the question, this guinea pig, what influence does it have in generating this guinea pig? Well, it has a big influence, this one here and this one here. So in the history of path analysis, one of the innovators of path analysis called this to be a causal coefficient. Okay, called it to be a causal coefficient. Why? Because it had a causal meaning given the context, right? Given the context, this had a causal meaning. This guinea pig is causing the offspring guinea pig. Now, the example historically is in terms of genetic transmission and heritability and things like that. But you get the idea as to what kind of license Sewell Wright, who came up with this, had for saying this is a causal coefficient. In other words, the system here was pretty much closed. Okay, it's not completely closed, but it's not bad. It's pretty much closed. What else could be producing the guinea pig? What else could be producing the color of the guinea pig? What else could be producing the height of the guinea pig when it's born, etc.? Those are influences from the parents. So this idea of calling these causal coefficients kind of made sense. Still philosophically very, very hard to figure out, well, what does that mean? Is this a partial cause? If something causes something, doesn't it always cause it? What does 0.3 even mean in terms of a causal coefficient? The issue we won't talk about here, but nonetheless, calling these causal coefficients had some merit, at least, even though it was debated by many people. And to this day, even in this context of biological variables, it still kind of seems kind of foolish to call it a causal coefficient, but that's where it came from. Now, when we talk about the general method of path analysis, it gives us no right to call these causal coefficients. So that needs to be clear from the start, is that if you take two variables here and make them predict this variable, nothing in any library will give you methodological right to give this coefficient any name of causality. You have no evidence that this is causing this one. The evidence that you could have would have to come from the context of the design and the context of the variables. So that might come from an experimental design, or it might come from a situation like this, where you say, well, what else could be producing the height of the guinea pig? What else could be producing the color of the guinea pig? What else could be producing the guinea pig? Say, well, we pretty much know that the mom and the dad here are producing the guinea pig. So calling it a causal coefficient makes more sense. But if I take arbitrary variables, X and Y, there's no methodological right to call that causation. So we need to be aware of that, especially when we get into models that try to call these things causal, that there's no evidence for causation unless you have evidence. When we talk about the multivariate regression as a path model, okay, so path models are relating all these observed variables to one another. These are all observed, and it's relating observed variables. That's what the path model is. If you think of a structural equation model, like we did previously, that confirmatory factor analysis is a special case of a structural equation model. Structural equation models will have those latent variables in them. So it'll have things like this. If we just restrict with observed variables, we're in the realm of a path model. And again, those are fuzzy distinctions a little bit, but in the literature, that's how it's generally defined. We've talked about the problems with assuming latency and stuff like that, but generally that's how they're defined in the literature. So the first thing that Mayer does here is identifies a model where we are going to fit a multivariate regression model. So it's multivariate because we have more than a single response variable. Right, we have a single response variable making it multivariate, so in that MANOVA spirit, and those are the number of response variables, Q response variables. This should look familiar because X is our matrix of variables, and then we have our regression weights, and then we have our errors over here. So this is the kind of like that big, most complete version of the general linear model, that instead of just xb plus e, we now have a big Y, which allows for y1, y2, a whole bunch of x's, x1, x2, x3, and then our coefficients associated with it. Okay. So there's several ways of computing the multivariate regression model, and one way is to stay in the classic linear model context. Estimate the regression model for each response separately, and then compute measures for MANOVA. Now, this is the multivariate analysis of variance, so you'd have to parameterize this a little bit differently, but we get the idea that we're in the multivariate idea. So the MANOVA model, what Mayer says here, could be a little bit misleading because the MANOVA model is not identical to the multivariate regression model. Because, you know, in the MANOVA model, your X is going to have levels to it for the different factors. Whereas in the multivariate regression model, these are going to usually be assumed to be continuous. You could operationalize it with levels, but it's usually going to be assumed to be continuous. You could also use a mixed effects approach, but if you wanted to specify random effects, which you don't always want to do. So we start off with a MANOVA here, and there's our equations that we're modeling. In this particular case, what Mayer is using here is a C-bind statement to bring these two variables together. So, when you do this type of thing, there's different ways of coding this. You could actually, instead of calling this into the function statement, you can even say y is a function of the C-bind. You put the C-bind right here and just generate y, and then write your statement as y is a function of A1, etc. It generates parameter estimates right here, and we see that these are statistically significant. This one isn't for A1. And you recognize some things from here that we're dealing with the Pillay test, which you remember from dealing with MANOVA. So there's Pillay's trace, looks familiar. Roy's largest eigenvalue, Roy's largest root is another name for it that we've talked about in the MANOVA context. We've talked about the decomposition of the sums of squares and cross products matrix into regression and residual. Now, when we talked about that, we didn't talk about it in terms of regression because we're in the strict MANOVA context, but this is the same idea, right? We're decomposing that multivariate matrix that we've talked about. Just to recap, that was in the spirit of discriminant analysis where we talked about the MANOVA model. Okay, so I know a lot's going on here, right? We talked about discriminant analysis, and remember I said, hey, mean vectors. Remember that part? I said mean vectors, let's talk about MANOVA. This is relating that to those ideas. So the context is getting pretty wide here. And this is what it looks like in terms of a path diagram. So these are observed variables. We have these observed variables predicting the responses. There's weights over here. And we also have covariances over here. And there's a covariance and the path. What did we say? One of the paths was not statistically significant over here. So you can look at the paths that are, the A1, right? A1 over here was not statistically significant over here. So the path model here is the purpose that Mayer is showing us here is that these path models can be generalized to incorporate classical statistics. And this is the multivariate regression as a path model using the unstandardized parameters. And you can kind of look at that in terms of a path model. Again, you don't have to. You can just run the regression and read off the parameter estimates like we typically do. You don't have to draw the model. There are some dangers in drawing models like this. When we draw a model like this, y1, y2, and then go x1, x2, well, we're kind of keeping it innocent, right? Because we're saying this is a function of this. You got to be careful here that you don't ascribe too much meaning to these weights. These are just regression weights. And the danger comes when you start saying this one is having an effect on this one. Well, if you want to say it has an effect, just recognize that this is just like pulling out your calculator and computing a coefficient. It's not having an effect on anything other than in the statistical sense, right? That's really important. So if you start putting variables here that you get too theoretically motivated by, right? You say, hey, I think this one here is going to affect this one here. Well, you don't have any evidence for that in here. Unless there's the parent guinea pig. And there's the baby guinea pig. Then all of a sudden, the height of the mom guinea pig may be having an effect on the height of the baby guinea pig. That's reasonable, but that reasonableness is not coming from the statistics. That's really, really, really important. The reasonableness is coming external to it because we know something about heredity. Because we talk to the biologist, and the biologist says, yeah, you're darn right that there's something being contributed by the parents. Everything we know about genes, there's some contribution. But if you just take this to be X and this to be Y, and you get a path that's statistically significant and all the rest of it, you can't say that X is determining Y or X is having an effect, like a biological effect or anything on Y. So I hope that's really clear. Is remember, pause and think for a second how minimally useful this model is unless you do not have some kind of a theoretical backing for these relations. Okay, it's minimally useful unless you have some kind of variables that maybe are meaningful that you can suggest stronger conclusions. The statistics do not make the conclusions for you. It's just like if I computed something on my calculator right now, 2 plus 3, it's kind of meaningless unless I'm, calculating something of meaningfulness, like whatever the case is, then all of a sudden the 2 plus 3 has meaning. That's really important. And historically, when you look at how structural equation modeling has come about, that can get a little bit dangerous because sometimes we ascribe too much meaning and the causality idea and all the rest of it. Well, that brings us to these moderator and mediator models. Well, the moderator is interaction. Okay, so when you think moderator, all you're talking about is a statistical interaction, but with the moderator, you're looking at if you have a quantitative idea. Careful with these words effects, right? It's not directional unless you have substantive meaning behind it. But if I have a variable here and I have x and y, I can say that z moderates the relationship between y and x if maybe the slope does this. In other words, the slope of x and y is steep, less steep, and then maybe it turns to negative. It's being moderated by z. But using the word moderated, again, be careful. There's nothing physical going on. Why call it moderated? Why not just call it there's an interaction? Careful of the power words, because if you use that in a thesis or dissertation defense or something like that, and you start prescribing physical powers to your variables for which you don't have, then you're being run by the statistics. And you've kind of fallen trapped into the idea that the statistics are able to inform you of a physical process. But the statistics do not tell you about physical process. You have to come to the statistics with a physical process already established if you're going to talk about a physical process. Remember, all the statistics are doing is partitioning variability and estimating parameters. Okay, so there's our moderation idea and looking at slope differences. Now the other one is the mediator. And if ever you do a moderator idea, you're going to have to choose different values of z in order to compute simple slopes and things like that. So it actually gets fairly involved. And there's actually like books available solely on moderated regression that cover a lot of the details of it. So if ever you go into something like that, recognize there's a few specifics you need to be aware about that are not covered in MER. The mediator model, be very careful about this. So as soon as they talk about the causal steps, well, Barron and Kenny is the classic resource for this. I'm going to be fairly critical on this because there's no causality unless you have causality in your model. So the idea here is if you have a network of variables, okay, if you have a network of variables like this, well, I guess I can just go to this one. If you have this network of variables, work intensification, emotional exhaustion. Does intensifying at work cause emotional exhaustion? Well, we don't know based on a correlational design, right? We just don't know. We don't know. However, if I told you that this model is completely perfectly specified, okay, if I said this was completely perfectly specified, in other words, that whole, I say we're modeling something and there's a whole bunch of other variables around that we're ignoring. Imagine if we had them all, this was it. Almost like if I give you the COVID medication, it heals you, right? The COVID vaccine, if this is the vaccine and it heals you, it's a pretty well specified model, right? I could almost say in that case there, Well, I still wouldn't be able without the experiment. I'd still need to do the experiment, right? Everyone see that if I give you the COVID vaccine and it heals you, well, maybe you would have healed anyways, right? It's possible you would have healed anyway. So do I have evidence that the COVID vaccine is causing the healing? I don't, even though it's so tempting, right? I mean, we're talking about even with biology, it's so tempting to say, you know, I gave you the vaccine and you got better, or I gave you the treatment and you got better. But you would still need an experimental design where you have control and experimental to know whether it's the vaccine or the medication that is causing it. Because maybe you'd have just got better anyways. So even in that circumstance, you need the experiment. So definitely here, we're dealing with non-biological variables. It's hard to even measure these things. That if I take this and I say it predicts this, I'm not going to be able to talk about any kind of causal path unless what? Unless maybe what? Unless I know for certain this is the complete system of variables, right? Almost like if the COVID idea, if this is the complete system of variables and I had no external influences, there's no external influences on the model of interest, then I may be getting closer to the idea of causation, just the mere idea. Whether you can actually talk about causal steps is still debatable, but at least it's more convincing. Please appreciate that point, is that if it's perfectly specified, well, then maybe you can actually start talking about something. Now, let me give you an example of a basically borderline perfectly specified model, okay? This is kind of extreme, but it works because you'll be able to compare all this to the perfectly specified model. So this person here, and you have a person here, okay? This person here throws something at this person here, okay? Throws something and it's heavy enough that it knocks this person down. So this person now is on the ground like that. This particular model is pretty well specified, okay? And what we mean is that this path here, this path, we could probably assign it some level of causation. Say, you know what? I know what produced this person to go down. It was the throwing of the rock going this way. But even then, right? And that's, I mean, look, like police officers and the law do that all the time, right? If this person shoots this person and this person dies, no one's going to come in and say, well, geez, I don't know if the model is correctly specified. Can we really assign causation? Now, the lawyer is going to say, look, I think we have causation here. This person caused this person to die, right? So there is very, very specified. Only in extreme theoretical ideas where we'd say it's not. But it's specified enough that we can draw a conclusion on it. Now, why is that specified? Well, because it's like, well, what else happened? Well, maybe it's this person, you know, you can say this person's resistance for the rock that was thrown at them, if they were stronger, or if they were wearing like a bulletproof vest, then they wouldn't have died, or they wouldn't have been shot. The bullet wouldn't have penetrated. So therefore, it's not really the bullet that's causing this person to die or to fall to the ground in the case of a rock. It's the fact that this person left their bulletproof vest, there's the bulletproof vest, at home. And what a world we would live in if the conclusion was, well, you know, it's not really the bullet that caused that person to die. Next time, take your bulletproof vest with you. But we don't think of things like that, right? Because that would be completely silly to think like that. We think that it's the bullet that caused the person's death, or it's the rock that caused the person to fall down. Well-specified model. Even though it's not perfectly specified. So there's still, on a theoretical, questions of specification. Now, when you come here, what do we have? Work intensification, we have no evidence that it causes emotional exhaustion, not based on the statistics. So when you compute the model and you compute statistics on here, these statistics cannot be determining causation or any other action word. The statistics cannot determine the action words. Okay, so stat does not equal action. And by action, I'm talking about things like causality. I'm talking about things like mediation, talking about things like moderation. Any kind of action word that you assign to this coefficient has to be supported external to the statistics. Okay, the support has to be external. Just like in this situation, it's external. It's not this coefficient for which we're assigning the action to. It's the fact that we looked at the setup, we said, well, yeah, it kind of seems reasonable what happened here. That's the same idea here. So even though you can measure these coefficients, if you want to make a stronger conclusion other than them being regression coefficients, you have to have a theory that backs that up. Just like the theory here, we had a theory. You have to have a theory here that backs it up. Otherwise, it's not enough to just compute mediation and conclude a physical process. That's really, really important. Now, sometimes you have good evidence for that, or it's so kind of convincing of a situation where you may want to make that argument. Like, I think it sounds reasonable that if I, work 20 hours a day and get 5 hours of sleep, I know you're saying that sounds a lot like graduate school, but if I work 20 hours a day and get 5 hours a week and I get exhausted, that may be kind of reason for me to say there's a causal link. And I think we'd all agree there's some kind of a directional link. But again, that's coming from the research area. That's coming from us knowing something about how these two kind of associate. And it could also come from your clinical experience, right? You're setting up the model based on your clinical experience of what you've seen over years of doing therapy, where you actually think there's a causal link. But again, it's not coming from the statistics. So even though I put this in as a mediator, okay, and the mediator, what are we talking about here? We're saying, well, there's an indirect effect of X on Y through M. Now, through M, I'm not quite sure what that means, right? Through M. How does it go through M? On a scientific basis, you would need to defend that somehow. If you're going to say work intensification goes through cognitive appraisal to emotional exhaustion, Dr. Fauci and Dr. Birx are going to say, what does that mean? Right? And they're going to say that not to be too critical, but they're going to say, how does that work exactly? What evidence do you have to say that it goes through M? And if you cite your mediational analysis, that's not enough to justify the process. Okay, it's not enough to justify the process. You should justify the process external to the model. Because look, it's perfectly reasonable that instead of using cognitive appraisal, I use just Z. What if I typed in values for Z into my computer and put that in here? And what if I found Z to be a mediator? Like I literally did this in SPSS, I put Z. And I found Z to be, I found evidence for statistical mediation. Have I established evidence that this variable is going through Z? No, I haven't. What have I done? All I've done is I've put in Z into the model. This coefficient, which was originally C, has now dropped to C prime. It's decreased. So what I have here is that correlational idea of a spurious correlation, that this correlation here is being explained by this variable. But if this variable is an unknown variable and something that I made up, something that I don't even know what it is, it's just Z, then I certainly don't have evidence that this variable is going through Z, because I don't even know what Z is. So we need to be careful when we use that language. And I'm not saying the language can't be used. I'm saying if you use the language, you should be able to defend the context. You should be able to defend the context. That work intensification leads to, if you want to use those power words, but it goes through cognitive appraisal. You have to have evidence for it external to the mediation model. That's the point. Some cases, people present really nice mediation models and say, that makes a lot of sense. Now, there's no experiment here, so there's going to be those limitations. But sometimes you can look at the mediation model and say, that kind of seems reasonable. Whereas other times, it kind of seems like a little bit far-fetched, like, where's the evidence for that? Now, again, Dr. Birx and Dr. Fauci, they're going to grill you on that a lot more. They're most likely not going to say, well, that kind of makes sense. They're going to go, you have no evidence that cognitive appraisal, whatever through means. So we need to be aware of that. Now, here are the equations for the single mediational model. So the mediator, that's the cognitive appraisal here. There's an intercept value because it's a regression equation plus AXI. So there's the work intensification. There's my X value plus an error term. So you have one equation here. And then you have the other equation, which is the emotional exhaustion plus the C times XI plus B times the mediator plus E2. So we use C prime for the effect of X on Y, A for the effect of X on M, and B for the effect of M on Y, and there's the intercepts. And we say that the indirect effect of X on Y through M is simply AB, this one times this one. But again, we want to be careful of the verbiage here. And there's nothing wrong with the verbiage so long as you know what it's actually talking about. The indirect effect, well, that's a statistical effect, right? This is just A times B, right? Just because you find evidence for the indirect effect does not mean that this variable is somehow physically going through this one. And again, even in this exam, I'm not quite sure how it would look to go physically through. Like, in other words, you have to know what through M means if you're going to use that word. Otherwise, all you're doing is doing this predicts this and adding this into your model. What does that sound like? Y, X, add M. What have you done? You've done a hierarchical regression. X predicts Y, observe the path, then put an M and observe the path. This goes to C prime. It changes, drops in weight. Full mediation goes to 0. Well, that's never going to happen. Partial mediation, it drops a little bit. But again, if you don't have the substantive support for it, then it's a hierarchical regression. And you don't have any evidence for these paths having any kind of physical connotation. Sewall-Wright with the guinea pigs, remember that paper? Sewall-Wright did have evidence for that. Now you can say, look, let me draw a model here for Sewall-Wright. Let's see, this is H. So parents, the 2 guinea pigs, and child. Maybe it's parent height or parent color or something like that, some kind of genetically transmitted process that the biologist says exists and that we have some evidence for on a physical level. Well, in that case, parental height predicting child height, maybe that's going through heredity. It's going through the mechanism of heredity. It's going through like, and I'm not a biologist, but it's going through like DNA transfer of information, etc. So maybe in that context, you write up a model like Sewall-Wright did, and you can ascribe maybe physical connotations to these coefficients. And maybe you can here too, I don't know, because I don't know this area, but you should be able to defend that if you're going to fit that model. What you don't want to do is simply just represent the mediational model and say, I did a mediational model. You want to explain to us why you think there's something going on. And that something going on is not in the statistics, it's external to it. It has to be, because the statistics can only partial out variability and estimate parameters. It can't do anything more than that. Okay. Now we get to the structural equation model formulation here. Let me see if I can just pull one up. So here's our full case of the structural equation model. And we have our factor here, our latent variable. Here's our latent variable, and we have different indicators. So this whole thing, you know, and you're setting up this theory for it, right? You're setting up the theory for it, is you're going to fit a model like this, and then you're going to assess the model fit. Now, in all of this stuff, and again, it looks sophisticated and everything like that, but really, you have to ask yourself, like, what's really going on here? And all it is evaluating that particular fit, right? How well can you regenerate the matrix, the covariance matrix, based on how you've chosen parameters? And you know, what parameters? Well, you've estimated all these of what parameters should be estimated. You specified your variables, and now you're going to assess model fit. And if you look at that and you think of, you know, that does sound a lot like the exploratory factor analysis. You see that, you know, you're really dealing with something very similar, because what was the job of exploratory factor analysis? Well, it was also to reproduce the covariance matrix. How did you reproduce the covariance matrix? You did by selecting, in the context of DFA, it was this, right? The lambda. It was that lambda matrix. And what did lambda matrix contain? F1, F2, F3. And you had to decide on the factor structure. Was there one factor, two, etc.? What kind of, you know, you maybe want to do some rotations to sharpen the weights, all that. But you were making these decisions so you could reproduce this. So you see that when we're doing the EFA, or we're doing a CFA, or we're doing an SEM, we are doing something remarkably similar in each case. If we're doing a path model, we're also doing something very similar. If we're doing a regression model, or ANOVA, since we know they're almost the same, or a t-test, let's put in t-test there too, we're doing something remarkably similar. And if you read more into structured equation modeling, and you know, sometimes people become specialists in a different statistical procedure, and that's oftentimes where research tracks kind of veer off. Some people specialize in longitudinal models, and you know, they do longitudinal modeling for 20 years because that's what they do, and they get really, really knowledgeable about these models and all of their different intricacies. And if you go into structural equation modeling further, you'll generally see what one of the big authors in SEM is Kenneth Boland. And Boland found and established actually that almost all statistical models could be subsumed under this equality. So this equality that we're talking about here, you can place virtually all of these models in this particular context. So what a unifying theme for understanding statistical models, right? Imagine if someone said to you, hey, do you want to do an ANOVA? And you said, what, am I going to try to reproduce a covariance matrix? If somebody says you want to do regression, path, and you understand that what's going on underneath is trying to reproduce that data based on the theory, and there's your theory again. Sometimes the theory is elaborate, it's like this. Sometimes it's fairly simple in the t-test. Again, none of this mentions anything about design issues. Okay, none of it mentions anything about design issues. So the design is a separate thing. So you could be doing all of this stuff, but still not have a convincing design that's going to give you any evidence for anything. And that's a kind of a dangerous thing, right? Is if the idea that a little bit of information, it can be dangerous. Because if you start developing statistical models, the rug could be swept underneath you if the design and measurement features aren't there. And even by the measurement features, you've got this where you say, hey, I'm measuring a good look. I've got several indicators. Well, assess the goodness of these. Are these really indicating what you want to assess? If this is depression and this is the BDI, if this is a poor measure of depression or it's not tapping into what you actually want to measure, then just because you're putting this as a latent variable does not help things. And that could be a little bit like of an illusion too, because we say, look, I'm being responsible in measuring this construct by different indicators, but if these indicators aren't good, this is completely hypothetical to begin with, so you got to be careful. Okay, so in all of this, there's still no control group. There's still no way of holding constant all of those other variables, and you're still in the universe of variables. So here are all the other things on the outside, that could be impacting all of this stuff that's going to change these from what they currently are. This does not exist in a vacuum. We draw it in a vacuum, but you cannot speak of it in a vacuum unless you have a context for which talking about it in a vacuum makes sense. Like that person throwing that object. That, in that particular instance, almost exists in a vacuum, or at least it's arguable. It makes sense. Why? Because this person who threw this at this person is going into jail for a crime, because it kind of makes sense. But here it's much harder unless these variables are very, very well defined and you can make that argument. So it's good to always compare how well those two kind of match up to one another. Because this here, you know, we have the regression. We know that putting x2 in changes that weight. It changes that weight. And again, there's the basis of the mediation model, right? I just drew the mediation model. There's the mediator. It changes the weight. That's all the mediation model is doing on a technical level. Okay. There's, for this particular model that we just did, there's our chi-square is 1.86. There's the degrees of freedom, and the p-value here is equal to 0. And you can obtain some other things in terms of the standardized fit statistics, et cetera, and look at your regression coefficients for that model that we just ran. Okay, so that's it for structural equation modeling. There's an overview of it. And so we talked a little bit about path models, talked about structural equation models. And what we're going to do next week is we're going to finish off the course. So next week's our last class, and we're going to talk about cluster analysis. And then it's going to be the final exam. So that's it for this week. What I would suggest you do is when you're looking at this stuff, you will get something on your final exam that has to do with this stuff, but it's not going to be like something that trips you up in R or something, okay? Because I know sometimes computing in R and you know, trying to figure out code, there can be delays in that, and that could be really hard. And sometimes you've had to contact me and say, you know, this isn't working. That's not going to be like that on the final exam, because the final exam, you only have a few days to do it. So whatever problems are given in this particular context of these models is not going to be something that you have to kind of figure out in R. It's going to be something you have to know about the models or can look up about the models in the book, but it's not going to be something like a tricky computer task or anything like that. Okay, so that's it for this week. And next week, we are into cluster analysis, and cluster analysis brings us back into the James text. Okay, so we'll see you next week.